Yes, but it wouldn't make any difference. No one looks at the study guide, so.
Hey, actually, I do look at the study guide.
I do look at the study guide.
See, he's giving you.
Okay, discrete and integrated voltage regulators. So this looks like an English. This looks like an English thing now. We have discrete things and we have integrated things. So a DC power supply has some filter output and it needs some regulation. And it needs to be predictable, and depending on the load, it's got to maintain the load either way, right? So I can't have a voltage supply that if I turn the power switch on, the voltage drops in half. That won't do me any good. So I need that. So I have an unfiltered guy. I rectify it, and I get the positive half cycle. I filter it, and I get the ripple to be less. And then I throw in voltage regulation, and now I have a DC guy going straight across. The problem is that the straighter that line is across, the more power I'm dumping the ground to get it to be straight across. Okay, so I want to make sure that if I put in 75 watts, I'm getting close to 75 watts out. It won't do me any good to put in 75 watts and get 12 watts out, because that'll just cause my thing to go up. So I got I have an ideal voltage regulator. It doesn't matter what the voltage in is. It can go plus and minus some voltage, and that's perfectly okay. But I have a constant 10 volts DC to the load with no ripple. And it doesn't matter if I double the load, I still have 10 volts. And now clearly there doesn't exist an ideal voltage regulator in the world. So we build them as best we can and charge as much as we can get out of charging them, right? And well, the big screen TVs that we repair, it's always been a power supply. It's never been the rest of the electronics. It's always been the power supply. So we have line regulation. There's a change in DC out divided by change from DC in. If my change in DC out is 0, then my line regulation would be 0. I don't have any change at all. We want this to be small. 1% would be nice. 0.1% would be nice. 0.01% would be nice. Each of those requires a doubling of cost. And doubling of cost is not nice. We could also have load regulation. As I increase the load from full load to no load, then I look at the change in current. Did the current go down? So this thing's got to provide current too. I'm putting those loads on in parallel. I'm adding more current coming through the power supply. Load regulation has to do with change in from full load to no load current divided by the change in the voltage divided by change in the current. No load's always going to be a higher voltage than full load. Voltage always going to droop a little, so this is going to be a positive number. And then we have a combination of the ratings. So I have some rating that is a line rating and some that's a load rating. So one voltage regulation formula goes, the voltage in can do that, the current out can do that, the regulation is 0.33. And I'm sure we'll have to do that calculation again. So now I can have series regulation or shunt regulation. Guess what happens when I'm in series? Well, I throw something to ground. Guess what happens when I'm in shunt? I throw something to ground. Doesn't matter in either series or shunt regulation. If I have something extra, I'm going to throw it into ground and get rid of it. Okay, shunt regulation on purpose. Series regulation still has some too. Those are my possibilities. All right, so I've got myself a common base type transistor sitting there, which means I'm not getting any gain All I'm doing is providing a constant current for the voltage that I've got. I have some Zener diodes so that I maintain a constant voltage on the base, and now I can draw more current through that transistor and still and maintain the voltage, and it's going to be whatever the Zener is minus a little bit. So that's perfectly okay. Now, clearly, if I want 1,000 amps to go through that transistor, I'm going to have a big one with huge heat sinks, right? And I have some of those. I have diodes in the lab that were designed to take 2,000 amps through the diode. It is about the size of my fist, a little bit smaller. So that's not a problem. I can build them that way. So now the voltage at the load is whatever the Zener is minus the base 2 emitter voltage, which is going to be about 0.7 or so. And but what's our problem? As the input voltage or the load current increases, the Zener diode must dissipate a higher amount of power. Okay, so that if we move back one, that Zener diode that's maintaining itself at a certain voltage is going to have to pass more and more power through it to maintain that voltage, and there's going to be some point where it's going to get burned out, also known as failing. And speaking of failing, I failed to only go one slide. So I end up, and now what I'm doing is I'm using a Darlington pair to maintain the voltage, and now I have less power having to be dissipated through the Zener diode, which is a good thing. Now I can use a smaller one. Series feedback regulation. Okay, so what I'm going to do is I'm going to make a thing that's going to sample my output current and sample the reference voltage on the way in, and it's going to detect an error and is going to go and change the amount of charge I can allow to pass by. Well, that's a good idea. I mean, to have boxes with no components in them. Boxes are very cheap. I can get a cigar box over here, and I got to put components in them. Yeah, I'm going to have to put some type of component in them. All right, so this is a series feedback guy. It doesn't look like I'm testing anything or sampling anything, right? No, it really doesn't, but that is what I'm doing. As the voltage goes up, the transistor notices that it went up, and now I'm changing what I'm doing. And so now I can have a series feedback regulation or voltage regulation. In the lab, we had, I have a power supply that's a 5-volt power supply that can put out 100 amps. Pretty cool, huh? Yeah, just what I need. I could put it in the back room and just run wires out to each workstation at 5 volts and not worry about you guys blowing a fuse or anything. I can have short circuit. I need short circuit protection. Okay, so it's okay to add another load, right? That's one thing. But what if somebody drops a hunk of 8-gauge copper across the circuit and grounds it? What am I going to do now? Am I just going to allow voltage to keep on going, current just to keep on passing and everything burn up? Or am I going to have some current limiting device associated with my voltage regulation so I don't destroy my power supply because of idiocy like me? So yesterday I were doing device net stuff with Scott, and I had all kinds of sparks flying all over the place as I was hooking wires onto things because he had it wired wrong. But luckily, the Allen Bradley stuff has current short circuit protection associated with it all over the place, and it didn't, even though I was shorting things out, it didn't care. Well, it probably cared a little bit, not a whole heck of a lot. So here we are with short circuit protection combined with series regulation, it looks like. So right there is my current limiting guy. I'm going to limit some current going through that resistor. If I have too much current, then my base is going to shut this thing down. My Q3 is going to shut down Q1, and then I'm going to stop sending things. So now I have current limiting. Do we see how that might work? The voltage across that itty bitty 1 ohm resistor builds up, turns this guy on or off, turns him off probably, and then now I end up changing the voltage, turns him on, change my voltage instead of going to the base now goes to ground, and I end up saving the day for a mere 50 cents in parts. Yeah, I can do that. So shunt regulation. A circuit has a regulating transistor in parallel with the load. Shunt feedback, a circuit is using error detection. Alright, so here's shunt regulation, and I go and I turn on Q1. That gives me a short and sends my extra current to ground, and isn't that lovely? And that keeps me from keeps my voltage right. Now normally your voltage regulators are all one part, so all these things are sitting on one chip, a voltage regulation chip, and we have several of them in the lab with a specially designed screw hole to hook it onto a big heat sink. So voltage regulation is normally done with a component, not multiple components like we're showing here. So over voltage, I can have shunt regulation. I can have a crowbar circuit. And I can have a crowbar as a fail-safe circuit that is designed to protect voltage-sensitive load circuits from excessive input voltages. Does that mean like lightning? No. Does that mean like electromagnetic shock from a nuclear weapon blowing up? No. But it does mean from the normal everyday things that you do that you are capable of doing, right? Like taking, for example, let's say I got this thing I'm going to plug into 120 volts, but my dad just changed the wiring in the house, and now the house is at 220 volts, and I plug it in. Is any of my consumer electronics going to work now? No. Are my industrial electronic stuff going to work now? Yeah, it will. All the Allen Bradley stuff works on a 120 to 230 volts. Doesn't care. And some of it doesn't care whether or not it's AC or DC. They over-designed it so it goes both ways. So here we go. One lousy integrated circuit with an input, an output, and a ground, doing all my voltage regulation in one lousy chip. So now I don't have to worry about any of the components inside, with a great big hole, with a great big metal heat sink associated with it. That's what a voltage regulator would look like. It sort of looks like a diode. Not a diode, but a transistor. It's got three things, right? And then 7805. So what does 78 mean? Who the hell knows? Somebody put a 78 on, right? 05, 5 volts. So if I have a 7812, it would be a 12 volt voltage regulator, a 7811, 11 volt voltage regulator, and so on. And that makes things worthwhile. Probably the 78 has to do with how much amps it can handle. Probably. Maybe it'll tell us later on. So I have 4 types: fixed positive, fixed negative, adjustable, and dual tracking voltage regulation. So, and as I move down the list, my price goes up. So negative, positive, I'm just going in and putting the diode in a different way. I have an NPN or a PNP. Adjustable means I have more parts, so I can have a voltage range. Dual tracking means that I just spent twice as much as I needed to have a voltage regulator. But if I was going to make something for the government or the military, that's what I'd want to do. All right, here are my the 78 chips and Motorola chips and who's LM, I forget, and other guys. And if I could read any of this, it would be really wonderful, but I can't. So we have a specification sheet, we have a minimum and maximum voltage, and we have symbols, and we have all kinds of things, and they're great. I see regulation special. Okay, so we have some dropout voltage, the minimum allowable difference between the input and output. We have a quintessent current. No, that's not quintessent. There's no S, there's no T in it. What is that word anyway? Well, I don't know. Maybe it is quintessent. Quintessent. Anyway, must be French. The portion of the regulator input current that's not diverted to the load. Sounds to me that fancy way to say I just threw it away. Ripple rejection, the ratio of the regulated input and output ripple, normally given in dB. Oh, that's good. So there's my load, there's my filter and my rectifier type stuff of my power supply, and then I throw in a LM317. The 17 is probably 17 volts. I'm thinking that that's probably what it's doing. And then I throw in another capacitor just for good measure, and I go to the load. Input-output voltage difference. Oh, wow. The voltage difference is the voltage out minus the voltage in, or the voltage in minus the voltage out. Who would have thought? Who would have? How come they voltage difference? Voltage in minus voltage out. Wow, awesome. I might even been able to do that. Output voltage adjustment. So I have a potentiometer on that circuit, and I've got some reference voltage, and I can adjust the voltages R1 and R2, the resistors R1 and R2, and I can change the voltage that I'm getting out of this thing. Isn't that lovely? I can go and put it in an AC circuit. So now I've got an AC circuit. I'm using fixed positive and fixed negative because one side of this is giving me the positive half cycle, the other side is giving me the negative half cycle, and then I'm throwing in capacitors to take out the filter, and when I get done I have plus and minus DC. Isn't that lovely? Just a dual power supply. I hope I told you how we do that in the lab, but if I didn't, you'll have to figure it out later. Okay, so guess that covers everything. Are we done yet? No, not yet. All right. So now we're going to go to switching regulations. Okay, so back in the good old days, 10 years ago, our power supplies were pretty simple. Now, if you want a power supply for your computer at home, it's a switching power supply, and there's not a damn thing you can do to fix it because they made it too complicated. Is that nice? Yeah, typical. So what I'm going to do is I'm going to throw in a bunch of digital circuit stuff to activate the gate on this transistor to allow current to pass to maintain the voltage. That's what I'm going to do. And it's going to be a digital thing that I'm sending there. And if I have more highs than lows, and this is open more and more goes through, I got an error detector that's telling me how quickly I got to do it to make it better. And I got a whole lot of little components that are surface mounted that I can't take off if they break. Now, why did I do that for? Everything was so fine with just 4 diodes, a capacitor, a voltage regulator. Why go to switching regulation anyway? It must have been the federal government must have got involved, right? That must have been it. The size of our magazines was limited, and we could only have less than 20, and now we're stuck with voltage regulation. That must be it. Either that or someone saw a way to make more money. That's probably more like it. So here we go. I've got some filtering system going on. Isn't that lovely? I've got some operational amplifier turning some gate on with some oscillators. So my oscillator is going all the time, and whether or not I allow it to turn on the gate will depend on whether or not I need it to turn on the gate. And I'm sending my output into my input into the output. Now, notice what's not happening. In all our other forms of regulation, we were maintaining the voltage on the output by throwing away current. Am I throwing away current on this one? No, I'm not. So that's the beauty of the switching power supply. I'm not, if I have 100 watts coming into my switching power supply, I've probably got 100 watts or 99 watts going out of my switching power supply. I'm not sending a whole lot of power to ground, throwing it away. So in theory, I'm saving greenhouse gases, and I'm saving the planet by going to switching power supplies. As a technician, it's a pain in the butt, because now we can't fix it anymore. We just have to replace it, but that's okay. You know, we can live with that. If it saves the whole planet, we can live with it, right? Yeah. If it doesn't save the planet, then we don't like it at all. All right. So now the average voltage is going to be whatever the voltage in divided by multiplied by basically the duty cycle. That's a go back. So time on divided by time on plus time off. That's your duty cycle, 50%, 75%, whatever. And that's what's going to give us the voltage out, in theory. So here we go. We have a longer duty cycle, and we get more power out, but we still keep the same voltage, and then we have a lower duty cycle, and because we don't have much load. Okay, pulse width modulation. So we're going to vary the pulse width in order to maintain the voltage. Oh, isn't that lovely? Just what we wanted to do. Now, that's what our power flexes are doing. They're doing a pulse width modulation to change the frequency. So we can do a pulse width modulation to change the power coming out. That'd be okay. I can handle it. All right, so here we go. Variable off time modulating the pulse width of the control voltage is fixed, and the total time cycle is variable. So I'm going in. I got some error, and I turn on, and I turn off, and then I stay off, and then I turn back on. So in this portion of the graph, I'm drawing some current. Now I draw less current, so I don't go up as often. That's just all I'm doing. Some error signal. Switching regulation configuration. Okay, so I can have a step down regulation, or I can have a step up regulation. Isn't that cool? So I can actually have more voltage on my output than I do on my input. The power going in still has to be the power going out, right? But there's no reason I can't step up the voltage if I play my cards right. Well, anyway. Efficiency, 98.5 efficient. Whatever it is. What is it? Whatever that big number is sitting there. So so I got a 12, and this is the Motorola chip again, and it's 12 volts out, 750 milliamps output. But I have a 36 volt input. Wow. And so obviously I'm not throwing away. In a normal circuit, if you had 36 volts out and 36 volts in, 12 volts out, that means if I was using just a Zener diode, that would mean I'm throwing away 2/3 of the power to get the voltage down. So this guy is to be 98% efficient. 89% efficient. Whatever the learning deficiency is up here in the front row, yeah. All right. So there's my switching regulator. I'm putting it in a chip so you can't touch it. If it fails, you can't remove it because it's surface mounted unless you have $2,000 worth of gear. I did tell you that the guys in the ice house for the Union Pacific guys in Council Bluffs, that they do replace surface mounted chips. The technology does exist, and they are successful around 90% of the time. But basically, you have to go down and have the right square heater to go on top of it to melt all the contacts at the same time, pull the chip off, and then do the reverse process to put the new chip back on. But their technicians can do that, and do that. They do. But if you're not doing it on a daily basis, you can't do it. And if you didn't pay the $2,000 for the gear, you can't do it. Yeah. So if you're trying to use your $5 soldering iron that I had you buy, and you have 100 pins and you're sucking the solder away one at a time, that ain't gonna work. All right, switching regulators. Advantages: higher efficiency, built-in variety of configurations. Disadvantage: generates a significant amount of noise. Can you do it? I don't hear any noise. Slower in response to change in load demand. Design, it's far more complex, that's for sure. What are we doing when our windmills, we have 5,000 windmills in Iowa, right? What kind of electricity are they making? They're making DC. Yeah, so they're making DC voltage. What type of electricity are they sending from the base out of that thing? AC voltage. And they're doing that with switching regulation. They're changing the AC to a DC, basically in an inverter, and it's a switching thing, switching on and off. Yeah, that's what they're doing. And we took those to sea with me in the 80s. In the 80s, we had a set of 400 hertz motor generators, and then we had basically switching power supplies that changed DC into 400 hertz AC. And so for redundancy, we didn't want to not have the power to shoot the nuclear weapons off and blow up the world. That of course would have saved the world. Using our nuclear weapons would have saved the world from global warming. So it wouldn't have been so that would have been a good thing, right? Oh, we're done? Bummer. Now we got to do homework problems. Let's see, homework problems. What chapter are we in? 25.
Water expired. I think you're probably all right. Yeah. You got water poisoning.
Okay.
You got the very back one, the warm one.
Okay, we're going to start with number 7 on page 902. Maybe we will if I turn my pen around the right way. Okay, so we're in chapter 25, page 902, number 7. The voltage regulator experiences a 1.5 millivolt change in output voltage. When the load current increases 20 milliamps, change in current load. Determine the load regulation rating. Okay, so Is it change in voltage, change in current?
Yep.
It is? Okay, so we want change in voltage out, change in load current. It's either that or the other way around, right? So 1.5, who put that there? Millivolts, 20 milliamps. 3%? I guess I should use my calculator. 1.5 divided by 20. Oh, that was really good, 3%. 7.5%. Is that all there is? I mean, really? Well, load regulation, yeah. Yeah, that's all there is. All right. Can't work with that too much. Number 9. Good thing I picked easy ones. Determine the approximate voltage of the load for the circuit below. The approximate voltage for the load. All right, so if we have AC input, that means we have 120 volts, right? That's what it's talking about. So 120 volts AC. I'm going to put that. I come in across my diode dealy dobs, and we'll work the other way. The Zener diode says 6.8 volts, right? So the voltage on the load has to be that 6.8 volts from the Zener diode plus the voltage base to emitter. That doesn't look like a volt plus sign, right? So what's the voltage base to emitter? 0.7? Yeah, 0.7. So I'm going to go with voltage on the load, 6.8 volts plus 0.7, 7.5 volts. Well, that was number 9. Number 17. A power switch like the one shown in 2521 has the following values. Okay, so my voltage of power switch, is that a power switch? Figure, all right. So VN, 36 volts. T on, 12 microseconds. T off, 48 microseconds. Average volt, okay, so voltage average is equal to voltage in times time on divided by time on plus time off. So that's what we're doing. And I don't know what the figure has to do with this because that figure has nothing to do with this problem at all. 12 microseconds divided by 60 microseconds. 60 microseconds. That's 5, right? So 36 divided by 5, 7.2 volts. Is that right? 36 divided by 5. Boom. 7.2 volts. Is that it? Yeah, okay, so everybody agrees?
Yep.
The average 7.2 volts. All right. One last problem. Look at that. The next.
Back one page, 7.2.
Oh, what'd I do? Do I have permission to go on or not?
Yes, you do.
I do? Okay.
You do.
That's all that matters. I just needed permission.
All right, you got it. It's
Number 25. Now, one of these ought to be hard, right? A plus 5 volt regulator has a load regulation rating of 2 ohms over the range of 0 to 100 milliamps max. Express the load regulation of this circuit in volts per milliamps, in percentage, and in percentage per milliamp. So I got
What
to.
letters under the V?
In, may I say?
What? Who? Where?
Milliamps?
Yep.
Right. So we're gonna express this in volts per milliamps. Okay. So we're gonna do the volts per milliamp first. That's what we're gonna do. All right. So we got 5 volts per 100 milliamps.
I figured you go over there. Are you guys deaf or what?
What are you gonna do when they say yes?
Yeah, I think we'll go 100 milliamps.
I think we need to party in here, obviously.
0.05 volts per milliamps.
That's called a negative.
All right, so that'd be my best thing. Okay, now percentage. Percentage. Okay. Change in voltage out. Okay. So I could have 0 volts, or I could have what?
You have an eager young man and his dad want to see you.
Oh, okay.
Did you know you had a tour?
Well, maybe, but we normally get out of class and do it. Okay, we get to tour a student. I guess you guys will have to remind me to do this problem next time.
Oh, we'll work on that.
Save as. Reminding me?
Well, why don't you have Jacob go out and do it? He's pretty good with this stuff.
Thanks, buddy.
Oh, did you see it?
You just can't
This goes so fast, it's a blur now.
It's the bomb.
Big yellow bus.